Hi, my name's Olivia and I'm a PhD student at the University of Liverpool. I'm going to speak a little bit today about my choice to do physics at university and why I chose Liverpool specifically. I'll also talk a little bit about my choice to do a nuclear PhD project and what I am doing, which is using thallium bromide sensors to detect gamma rays. So, a little bit about myself. I'm from Manchester, and at A level, I decided to study English literature, physics, and maths. And I'm sure you can tell from that, I wasn't really sure what I wanted to do in the future. So, I kind of placed a bet and did English, maths, and science. But throughout my A2, I really started to enjoy physics. I really enjoyed the experiments that we got to do. And we also went on a trip to CERN, and I got a taste of these types of big experiments that you could do in a physics career. I wasn't very good at it at that point and I got quite low grades, but during my final set of exams, I managed to pull it up and I came out with a B. I then applied to Liverpool to do physics, and that's partly because I had the grades to get in there and it was a close university to my home. I wanted to go somewhere near Manchester that was also a big city, and Liverpool offered that for me. Initially, I thought I wanted to do medical physics, but as I started doing the courses at university, I really started to get interested in nuclear physics. I realised that the detectors that we use in nuclear physics could be used in medical applications for when we have X-rays, for looking at nuclear power plants and sorting out the waste there, but also for security purposes. So that's why I chose to do nuclear physics as a PhD. And my current research is based on using new radiation detectors for decommissioning power plants. So, what does that mean really? Well, I'll have a radiation detector that detects gamma rays, and different radionuclides will emit a specific gamma ray energy. So, if I can identify them, I could go into an old nuclear power plant that needs to be demolished and say there's cobalt 60 in one corner and there's cesium-137 in another corner, which both emit gamma rays. And this is important because these different radioactive isotopes need to be dealt with separately before we can remove them and demolish these old nuclear sites. Outside of university, I have lots of interest. I like rock climbing, which seems to be quite a student-focused sport. Lots of people in my office do it. I'm a Girl Guide leader, which I've done guiding since I was a rainbow at the age of 5. I do lots of baking and I really like science communication. This is something new to me. I only started it about 2 years ago, but since then I've written for physics magazines and managed to do outreach at science festivals and at the Museum of Science and Industry in Manchester, which is something I really enjoy. You get to meet lots of people and it's always a really positive experience. So, why nuclear? I spoke a little bit about enjoying nuclear because of all the aspects that it can be used for, like medical physics, security, energy, decommissioning. So, in my third year of university, I applied to do a placement at a university in America called UMass Lowell, which I was lucky enough to get. So, I went over there for 2 months. The university is just outside Boston, and I lived on campus and worked in their physics department. If you look on the left-hand photo, where all the people are, behind us, a big white building, is the nuclear reactor that they actually have at the university there. So my project for that summer was to characterise nuclear fuel rods using gamma ray spectroscopy. So this involved taking fuel rods out, which you can see in the middle picture, the bar that has got the blue tape around it, that is a fuel rod that is taken out of a reactor, and all the cones on the outside are gamma ray detectors. So I use those detectors to work out what exactly was remaining inside a fuel rod once it had been used for energy. This is important because we can't touch it with our hands, so we need to find other ways to work out what is inside the fuel rod so that we can dispose of them correctly. I was also lucky enough in my 4th year to get some funding to go on a trip around Europe and collect soil samples, which doesn't sound very nuclear focused, but it was related to the Chernobyl accident, which if you don't know, Chernobyl was a power plant in Ukraine that blew up in the 1980s, and lots of radioactive dust got spread across the whole of Europe. So I went around Europe to collect soil samples, brought them back to the university, and we were working out the activity of the radioactive particles that were left behind 30 years on. And so that was really interesting. That took me to Germany, France, Poland, Ukraine. I got to go to lots of places, which was an amazing experience. So I then decided to go and do a PhD in nuclear physics, just solely based on all these amazing experiences I've done, the people that I've met, and the fact that I really enjoyed the work that I got to do. So this is my PhD project. As I said, I've said before that I use gamma ray spectroscopy a lot. So what does that mean? Gamma rays are emitted from nucleus when they have too much energy. So they want to get into a more stable state. So they release gamma rays, beta particles, or alpha particles. Now, if I can identify the energies of the gamma rays that are emitted, I can identify which radionuclide emitted them. So if you look on the left-hand side, that's a fuel rod spectrum, and that is one that I took at the university in America. The two lines that are highlighted are from a cobalt-60 source. Now, only cobalt-60 will emit energies of 1773 and 1333 keV. So I will know from looking at any fuel spectrum that I've got those energies in those ratios, that cobalt-60 is definitely in there. Likewise, I can do this with other isotopes like cesium or uranium. So this is really useful to work out what is inside nuclear waste. Currently, detectors that are used to do this are really big. They have to be cooled by liquid nitrogen in order to work, which means we can't really take them into remote areas. So if you look on the right-hand picture, we have a nuclear waste container at Sellafield, which is where the UK keeps most of its nuclear waste. And it's quite busy. There's lots of difficult places to reach, and we can't really take in big equipment to work out what is on the walls of these containers, what's underneath certain things. So we need something small that can work at room temperature, that doesn't need all this extra equipment to work. That could maybe be put on a drone or a robot that could be flown in, and I survey the area. And that's where my project comes in. So if you look on the right hand side, that is my detector. It's made out of a material called thallium bromide, and it is 5mm by 5mm area and only 1mm thick. So this means that it is truly portable. And what's exciting about my project is that the crystals are grown by a company called Capesim, which are based in Boston. So although I spend a lot of time at Liverpool doing all my analysis here, I get to go over to Boston quite a lot to work on fabricating the crystals and building up my detectors. So a little bit more about how thallium bromide actually works as a radiation detector. If I have a gamma ray source, it'll emit gamma rays in all directions, and a gamma ray will come into my crystal and create electron hole pairs. If I apply an electric field across the crystal, the electrons will get attracted to the positive side and the holes will get attracted to the negative side because opposite charges attract. That then therefore creates a current, because current is just the movement of charge. If I plot a histogram of all the different charges I get out, there will be an average point around where the gamma ray energy is emitted. So I'll get a spectrum, just like I showed you here, where each gamma ray energy is a peak. In addition to this, I can also use the detector to calculate the activity of a radioactive source, which is dependent on the efficiency of the detector. This is then dependent on measurement conditions such as the source to detector distance, which changes with 1/r squared, and detector characteristics such as how much material I've got or how dense it is. And these are all considerations I have to take into account when I'm planning my experiments. So now I'm going to talk a little bit about how I actually make my detectors. To begin with, I have to grow the crystal, and we start with a really pure piece of thallium bromide in a crucible or like a test tube, and on top of that we put rubbish pieces of thallium bromide on top of it. And if we heat it all up, the good part of the thallium bromide that's really highly structured will translate along the crystal, and it'll all melt together, and we'll get a really solid, strong piece of thallium bromide with really good crystallinity that we can use for detectors. Now, these can be grown up to about 18 inches, which is really good because, as I told you before, my detectors are actually 1 millimetre thick. So we can get lots of detectors out of just one crystal growth. This means that my detectors are really cheap compared to other technologies that maybe can only grow 1 or 2 inches at a time. So after that, I have to cut my crystals, and I use a really, really thin wire saw to do this. And if you look in the middle picture, the yellow blob in the middle are slices of thallium bromide attached to a graphene block using wax. And the two wheels are holding a wire saw, and that just goes forwards and backwards, cutting through the material. And we have to put water onto it to keep it cool because it actually gets quite hot because it's travelling so fast. And on the right hand side, that is what they look like when they're cut. So I've got 5mm by 5mm detectors. Because thallium bromide is a really soft material, we actually get lots of ridges in the surface once they've been cut. So what I have to do is use an acid called hydrobromic acid to rub away the surface until we get it quite smooth. And after that, we can apply electrodes. And as you can see on the right hand side, this is the electrodes put on, and we've also attached some wires. We attach the electrodes using something called thermal evaporation, which is basically just heating up some metal until the particles fly off and then they become attached to the detector, or by sputtering, which is a similar process to thermal evaporation, except we use a plasma to heat up the source instead. Then we attach it to the electronics, which is as simple as using crocodile clips, and attach this to a preamplifier which extracts the charge, and then oscilloscope so we can see the charges coming out. And this is what my experiments look like. Not everything is really high tech at universities, and actually you can see my gamma ray source on top of the detector, which is a baked potato looking thing, which is essentially this wrapped up in tin foil. I had to do that because there was lots of noise in the lab and it was interfering with the signals I was getting out. And then this is all attached to the electronics, and that is attached to an oscilloscope. So this is actually the gamma rays coming from a cesium-137 source. So then if I plot a histogram of the height of all these gamma rays, I get a spectrum like I showed you at the beginning of the presentation. And from that, I can identify different radionuclides. So in summary, thallium bromide is a new material that can be used to detect gamma rays, and that is what my PhD project's based on. It's really promising because it works at room temperature, it's small, and it's really efficient at detecting gamma rays, which means I can use it to get into hard to reach places at old power plants before they're decommissioned. Currently, I'm trying to research into its material properties and improve the quality of the spectra that I'm getting out. This will make it easier to identify different isotopes in highly complex radioactive areas. And in the future, I hope that they'll actually be used for real power plants, not just in the lab for tests. Thanks for listening, and I hope you enjoy the rest of the course.